Okay, in this tutorial we're going to be looking at complex numbers in rectangular form. Okay, so there's a little bit of work to do in this section, but it's okay, we'll get through it. Okay, so basically what we end up with complex numbers when we're trying to actually find square roots and negatives. So in the past, when we've been trying to find the square root of say -9, okay, we've gone, no good. Okay, couldn't do it. Okay, basically what we do now is say, well, I squared equals -1. So that means then that the square root of -1 equals I. And we do that and then we just keep moving on. Okay, so for example, if we want to find the square root of -25, okay, well we can think of that as the square root of -1 times 25. Okay, and then we can say, well, the square root of -1 is really I. Okay, and the square root of 25, we can really say square root of -1 times the square root of 25 now. Well, that really gives us I times by 5, and we usually just write it with our coefficient of 5 in front. Okay. The other thing that we can do too, okay, is looking at solving the equation z squared plus 25 equals 0. Okay. For that, well, what we can do is we can really think of this, okay, is we can think of it as the difference of two squares. So we can think of this as z squared take minus 25 equals 0. Okay, so you can really think of that as, well, remember I squared equals -1. Okay, so we can really think of that as z squared take 25 I squared equals 0. Okay, so then we can say really that we've got, if we factorise that, or sorry, we can simplify this even, sorry. We can say that that's z squared take 5I squared, okay, because that will give us the same thing. Okay, I'm still equaling 0. Well, that means that we can say, well, we've got z plus 5I, z take 5I equaling 0, or that z equals plus or minus 5I. Now, a lot of people would have realised that we could have done that a different way, that from here we really could just say, well, z squared equals -25. Okay, well, z equals plus or minus the square root of -25, and we found that over here. So really z equals plus or minus 5I. But this is the way they did in the textbook, so I thought I'd show you that way as well, but I would do it this way pretty much all the time. Okay, we also talk about solving quadratic equations. So, remember, if we've got an equation az squared plus bz plus c equaling 0, okay, then and a, b and c are all real numbers. Okay, then remember the discriminant, which we use delta for, is given by b squared minus 4ac. And we basically use that, okay, this value of the discriminant, so we knew how many solutions we had. So remember, when the discriminant was larger than 0, well, we had two distinct answers. Solutions. Okay, if our discriminant equaled 0, then we had one real repeated solution. Okay, and in the past we basically said, well, if our discriminant was less than 0, there was no real solutions. Okay, that's how we've tackled it in the past. But now what we can say, okay, is that really that if the discriminant is less than 0, okay, then we have a pair of complex conjugate roots. Okay? So the discriminant is less than 0. We say we have a pair of complex conjugate roots. Okay? So we'll actually look at doing an example of this to find out what those roots would be. Okay? So what we want to do is we've got a little example here. Okay, so we want to solve for z if z squared plus 4z plus 13 equals 0. Okay, well we need to think, okay, how can we do this? Okay, so what we want to do is, in this example what they've done, I won't worry about method 1 because I don't really like method 1. Okay, what I want to do is go, well, if we look at our discriminant, okay, that's given by b squared take 4ac. Okay, well, b is 4. Okay, a equals 1 and c equals 13. Okay, so we say, well, our discriminant equals b squared, which is going to be 4 squared, take 4 times 1 times 13, okay, which equals negative 36. Okay, so if we find, we're allowed to then find the square root of our discriminant, which equals the square root of negative 36, okay, which equals obviously 6i. Okay, then what we can do is use the general quadratic formula then, which is going to be z equals negative b plus or minus the square root of our discriminant. Okay, the square root of our discriminant, which we just found. Okay, so just rewriting the general quadratic formula a little bit differently. Okay, what we could have done is just straight from here use the general quadratic formula. We've just broken it down a little bit more. Okay, because then we've got, well, b was 4, so a negative 4 plus or minus 6i over 2 times 1, which was 2. Okay, so then we can say, well, z equals negative 2 plus or minus 3i, just by dividing by our 2. Okay, so I'd probably just go straight for your general quadratic formula from here. Okay, we know it's a complex number. Okay, we're doing the work on complex numbers, so we know we're not going to be able to factorise it nicely ourselves, so may as well go straight to the general quadratic formula. You put everything in, the difference is you're going to end up with negative values for your discriminant, and you just sub in an I when you have that. Okay. So, complex numbers in rectangular form. A general complex number is represented by z, okay, and it's defined as z equals x plus yi. Okay, so we say that x and y are real numbers. Okay, so x and y are both real numbers, but z is a complex number. So x and y are elements of R, but z is an element of C. Okay, so C is used to denote the set of complex numbers. Okay, in the same way that R is used to represent all real numbers. Okay, so notice that z is actually just one number, but it's made up of 2 separate parts. Okay, but it's one number. So our x, okay, represents the real part. Okay, and y represents the imaginary complex part. So our imaginary complex part. Okay, so what we can say is the real part of z, well, that's our x, okay, and the imaginary part of z is our y. Notice we don't worry about using the I. Okay, so real part of z is our x, imaginary part of z is our y. Okay, so operations on complex numbers in rectangular form. So addition and subtraction. When adding and subtracting complex numbers in rectangular form, we add or subtract the real and imaginary parts separately. Okay, and we've got some worked examples coming up on that. Okay, and the multiplication by a constant. Okay, if we've got a complex number z, I'm going to multiply it by some constant k, okay, then we multiply both the real and the imaginary parts, okay, by the constant. So we'll look at a worked example. Okay, so if we have u equals 2 minus 5i, okay, and v equals minus 3 plus 2i, okay, then we're going to look at finding u plus v. Okay, so u plus v, well, that's going to be 2 take 5i plus negative 3 plus 2i. So we go, well, 2 plus negative 3 is negative 1. Minus 5i plus 2i is going to be minus 3i. So we're adding the real parts, adding the imaginary parts to get our solution. Okay, the other thing we're going to look at is doing 2u take 3v. Okay, so 2 times u, well, u is 2 take 5i. And we're taking away 3 lots of v, which is negative 3 plus 2i. So we're going to expand our brackets. So we've got 4 take 10i minus, well, we're 3 times negative 3, so that's negative 9, and minus 3 times 2i is negative 6i. So we've got 4 take negative 9 is the same as adding, so 13. Okay, minus 10i take 6i gives us negative 16i. Okay? Okay, next part is, we all know about the Cartesian plane. Okay, now we can also graph and represent graphically complex numbers, and we do that on an argand diagram. Argand diagram. Okay, it's just named after a Swiss mathematician, the Argand plane or the Argand diagram. Okay, and the way we do it, okay, is it actually makes a lot of sense. Okay, we put our imaginary part here and our real part down there. And I say that makes a lot of sense because if we look here, okay, our real part was our x. It's where we are used to our x-axis being. The imaginary part, okay, is y. Okay, so the imaginary part is where we think it would be. Okay, so then what we do, okay, is to represent it. Okay, then we just put on our points separately. Okay, and notice that we're on here. If we were to put a scale, we'd just go 1, 2, 3, 4, on we go. We don't need to put 1i, 2i, 3i, 4i. It's just implied. Okay, and same down here. We don't do anything differently. Just a standard scale. Okay, so if we're looking at geometrically with multiplying complex numbers, well, we might have had z equals 3 plus 2i. Well, we would have been 3 and 2i, so we would have been up here. Okay, so that's where our z is. Okay, if we were going to multiply z by some value k, so we then said, well, we had kz equals, well, we've got to multiply it all by the constant k, so it'd be 3k plus 2ik. Okay, and what that means, basically, is that we come across here, okay, by some value, k times our real part, or our x part, and we come up here and be k times our imaginary part. Okay, so we'd end up over here somewhere. Okay, so if we had that much, well, this is k times bigger. So if that is z, this is k times z, it's k times bigger. Okay, if we're adding in the complex plane, okay, this is like adding vectors. Now, if you're following along in the order of the textbook, we haven't actually got to vectors yet. Okay, but if we had some value here, okay, of z, we'll call that z2. If we had one here, that is z1. Okay, well, for z1, we're going to have some value here that is x1 and some value here that is y1. Okay, and for here we're going to have a value that is x2 and here a value that is y2. Okay, so if we want to work out what z1 plus z2 is, well, what we need to do is we need to add our x1 and x2 together. Okay, and that'll give us some value up here, we'll call that x3. We need to add our y2 and y1 values together. It's going to put us somewhere up here, we'll call that y3. Okay, if we track across and down, then up here is going to be our z3. So what we've really done is we've broken down our two z values into a horizontal and vertical component and a horizontal and vertical component. We've added our horizontal components together, we've added our vertical components together, and we end up getting our overall new value. Right, if we're talking about subtraction, if we want to do z1 take z2, okay, well this time what we do, okay, is we've still got our z1 that's over here, it's got our x1 and our y1. Okay, but remember that z1 take z2 is the same as saying z1 plus negative z2. Okay, and to make something negative, you change its direction. So where we had z2 coming up there, z2 is now going to come down here. Okay, and so this is our x2 here, and this is our y2 here. Okay, so if we add those two together, okay, well, we're adding a negative now, so our x3 will be here somewhere. Okay, and we're going our y1 take our y2, so we're going to be down here somewhere. Okay, yeah, somewhere there. Okay, and again track them together. Okay, and our resulting one would be down here this time at z3. Okay, that's very similar to vectors. Okay, if we want to multiply complex numbers together, so we actually want to multiply u and v together. So if we had u was equal to 2 take 5i and v is equal to minus 3 plus 2i, and we want to find uv. Well, you simply do it as you'd expect. Okay, put them in brackets. Okay, and expand your brackets out. So we're going to have 2 times negative 3 gives us negative 6. 2 times 2i is going to give us 4i. Minus 5i times minus 3 will give us positive 15i. Okay, and minus 5i times 2i is going to give us negative 10i squared. Now, the thing to remember though, by definition, I squared equals negative 1. So this we can make positive 10. So we can say we've got 6 plus 4i plus 15i plus 10. Okay, now we can collect our like terms. Minus 6 plus 10 gives us 4. 4i plus 15i gives us 19i. Okay? That's what we can do there. Okay, next up. Hey, what we can do is we can actually think of this in a general way. Okay, so if we said that z1 is equal to a plus bi, okay, and z2 equals c plus di, then z1 times z2, okay, is given by ac take bd plus ad plus bci. Okay, so there's a general solution. Okay, so what we can do here is go, okay, if we had u equals 2 minus 5i and v equals 2 plus 5i, okay, well, what's the real part of uv going to be, and what's the imaginary part of uv going to equal? Okay, so the real part is given by this part here. Okay, so we've got a times c, well that's going to be 4, take b times d, well minus 5 times 5 is negative 25, okay, which gives us positive 29, and the imaginary part is given by ad, okay, so 2 times 5 is 5, plus, 2 times 5 is 10, plus minus 5 times 2, which gives us negative 10, 10 take 10 equals 0. Okay, so we actually don't have an imaginary part when we multiply these two numbers together. Okay. Next up, we have complex conjugates. Okay. In work example 5, the complex numbers u and v, okay, have the property, okay, that the imaginary part of their products produce 0. So we're talking here. This was worked example 5. Okay. When we multiply these together, the imaginary part cancelled out. Okay. And these numbers are called complex conjugates of each other. Okay, complex conjugates. So if we do it graphically, with our imaginary part as z and our real part as z, okay, then what it looks like is this. Okay, that we've got up here we've got our y, and down here we've got negative y. Okay, so actually completely cancel each other out in the imaginary direction. Okay, so if this one here is z equals x plus yi, okay, then the conjugate of it, okay, is given by z bar. We call that z bar equals x minus yi. So complex complex conjugates is denoted as z bar. Okay, so read it as z bar. Okay. So if we actually multiply z by z bar, okay, what we find is, well, we get x plus yi, x minus yi. Okay, when we do that, we get x squared take x yi plus x yi take y squared I squared, okay, which equals x squared plus y squared. Okay, so that's what happens when we actually do it. Okay, so that means that the real part of z bar is our x squared plus y squared, okay, and our imaginary part of z bar is actually equal to 0, because notice we don't have any i's left. Okay, so there is no imaginary part. Okay, so and you can see here, okay, that z bar is simply a reflection of z in the horizontal axis. Okay, so the reason why we have that is because the conjugate is useful in division of complex numbers, because both the numerator and denominator can be multiplied by the conjugate of the denominator. Hence the complex number can be replaced with a real number in the denominator. This process is similar to rationalizing the denominator to remove surds. So what we're going to have a look at, okay, is worked example 6, which says, well, if u equals 2 minus 5i, okay, and v equals minus 3 plus 2i, okay, then what we're going to do is we're going to find, first of all, u to the power of negative 1, and in v we're going to find u divided by v. Okay, so remember, u to the power of negative 1, well that means 1 over u, okay, which means we've got 1 over 2 take 5i. Okay, so what you can do is, yeah, what we call, it's kind of like rationalizing the denominator. Okay, so what we do is we then want to multiply this by the conjugate of this. over itself. So 2 plus 5i over 2 plus 5i. So really we've multiplied it by 1. Okay, but by doing this, okay, we get 2 plus 5i over, when we multiply those together, we're going to get 4, take 25i squared, which is 2 plus 5i over 29. Okay, we can split that up and say that we've got 2 over 29 plus 5 over 29i. And that's something that you would do. You do want to split this up, because otherwise you go, if you're looking at this, you go, well, what's the real part, what's the imaginary part? Okay, so we need to split it up into our two separate fractions so we can clearly see which part is which. Okay, so that is our u to the power negative 1. Okay, for our second part, we want u divided by v. So we've got 2 take 5i over negative 3 plus 2i. So what we want to do is the same process as what we did here. Multiply it by negative 3 take 2i over negative 3 take 2i. So multiplying it by the conjugate over itself. So when we do that, okay, we're multiplying these two together. So we've got 2 take 5i times minus 3 take 2i over this squared. Okay, and when we do that, well, this bottom part is going to be 9 take 4i squared. Okay, our top line is going to become minus 6 plus 15i take 4i plus 10i squared all over 13. Okay, because remember this becomes negative 1, so it becomes positive 4, makes it 13. Okay, and we're almost there, because it means that we've got minus 6 plus 11i take 10 over 13, which gives us minus 16 plus 11i over 13. And again, we want to split it up, so we've got negative 16 over 13 plus 11 over 13i. Okay, so it's this process of multiplying by the conjugate. Okay, now we can do a general solution for this. Okay, general solution to dividing complex numbers. Okay, so if Z1 equals our A plus BI and Z2 equals C plus DI, then Z1 over Z2, well, that's going to equal AC plus BD over C squared plus D squared, okay, plus BC minus AD over C squared plus D squared I. Okay, so it looks a little bit horrible, but again, if you've got this general solution, okay, you don't have to go through this whole process. Okay, we're given a general solution, so we're allowed to use it. So if we've got these two numbers here, we could simply have plugged our values in here and just simplified. Okay? So equality of complex numbers. Two complex numbers are equal if and only if their real parts and their imaginary parts are both equal. Okay, so this makes a lot of sense. Okay, we can't say that two things are equal just if the real part is the same or just if the imaginary part is the same. Both of them have to be the same. Okay. So, solving equations involving complex numbers. To solve an equation involving a complex number, we rearrange the equation to find the unknown quantity, then use the same rules and strategies as when solving equations with real coefficients. Okay, so what we're doing for this one is we're finding the complex number z if 3 times z plus 2 over z plus 2i equals 5 minus 2i. Okay, well, as you'd expect, we'd multiply out the bottom line, so you've got 3z plus 2 equals 5 plus 2i times z plus 2i. Okay, expand out those brackets, so we've got 3z plus 6 equals 5z plus 10i take 2iz. Okay, take 4i squared. Okay, well, we simplify that a bit and say that we've got 3z plus 6 equals 5z plus 10i take 2iz plus 4. Okay, because our I squared equals -1, -1 times 4 gives us positive 4. Okay, we can keep rearranging here. Okay, and say that we've got 2 take 10i, okay, equals 2z take 2iz. Okay, so we can isolate our z now as well. Okay, so what we're going to do is we're going to take z out as a common factor from this side. Well, we're going to take out 2z actually, so we go 2 take 10i equals 2z outside of 1 minus I. Okay, so then what we can do is we can cancel out our, we take 2 out of this side as well, and so we've got 2 outside of 1 minus 5i equals 2z outside of 1 minus I. So that way we can divide by our 2's, say that we've got 1 minus 5i equals z outside of 1 minus I. Okay, therefore our z is going to equal 1 minus 5i over 1 minus I. Okay, we're almost there, because again we can multiply by our complex conjugate. Okay, and so we get z equals 1 minus 5i on 1 take I times by, 1 plus I over 1 plus I. Okay, and that's going to give us, when we do that, okay, it's going to come up here, it's running out of room, we get z equals 1 plus I take 5i take 5i squared over 1 minus I squared. So that gives us 6 take 4i over 2. Okay, and that gives us the final answer of z equals 3 take 2i. So it is very, very similar to what we would have done any other time. Okay, it was just a matter of doing a bit of algebra. We had to do our complex numbers section in here, like just knowing that I squared equals -1. Okay, from there we're just collecting like terms from rearranging, and then we just used our recent knowledge of this complex conjugate, okay, to simplify it further. So we had somewhere to go from here. Okay, so we're getting there. Okay, so the next part is to talk about powers of I. Okay, as we know, well, I squared equals -1. Okay, well then it would make sense then that I cubed, okay, would equal -I. Okay, because we'd be talking about breaking this down to I squared times I, and we know I squared is -1, so -1 times I, times I gives us our -I. Okay, if we go I to the 4, okay, well really you can think of that as I squared times I squared anyway, which is -1 times -1, which is going to give us +1. Okay, and then you'll find that I to the 5, okay, is going to be this times I, so that's going to just be I. Okay, so a pattern can be seen for repetitions of the power of I. Any even power of I will give plus or minus 1, while any odd power of I will give plus or minus I. So even powers will give plus or minus 1. Odd powers will give plus or minus I. Okay. So multiplication by I. Okay, so we have z equals x plus y I. Okay, then I times z, okay, is going to equal I times x plus y I, which is going to equal ix plus I squared y, which is going to equal negative y plus xi. Okay, what that does, okay, is it actually rotates graphically by 90 degrees our value of z. Okay, so if we've got z here, okay, saying that's z, okay, and this was our x, this is our y, okay, we rotate 90 degrees out this way, and this one, our iz, well that's our y that we had, and this is the x that we had. Okay, so it's rotated anti-clockwise around. Okay, so look, that's actually the end of this section. I know it's a fairly long section, so and it's a lot of new stuff. So look, I would probably recommend going back and watching it again, particularly while you're doing some questions, just so you can get your head around what you need to do.